Hi people, hope we're doing well today. Um, this is the video to supplement day one of inverse trig, where we were talking about inverse trig as a function. Usually I go ahead and repeat a lot of the conceptual and constructive aspects of the lecture. I'm not going to do that this time. I may go back and do it at a later date, but I'm hoping that the original explanation was sufficient, and since you have access to that, I'm just going to move through some of the problems. Okay, so let's go ahead and get started. Now remember that when we're dealing with inverse trig as a function, we are looking for a single answer. Okay. And so basically, if this right here is our, y is equal to arctan of x, then, we're basically just asking, if I have an input of 1, what is my output, right? Now, like I've said before, for functions, you can ask functions a whole host of questions, right? You can ask some input-based questions, you can ask some output-based questions. That's more when we're talking about solving the equations, and that's the operation-based stuff, and that will come here in just a little bit. But in this, we are looking for the one value, the one output. Because remember, as a function is defined as a relation wherein each input has exactly one output, no more than one output. Now, arctan, basically it's asking, where does tangent on the specified domain and range have a ratio of -1? Well, remember that tangent is the ratio of sine over cosine. And therefore, when sine and cosine have the same value, exactly the same value, like at pi over 4 and 5 pi over 4, it's 1. When they have the negatives of each other, when they're negative of each other, like at 3 pi over 4 and 7 pi over 4, it's -1. But remember that we have a very specified domain and range. Basically, we have, the domain on arctan is -infinity to infinity, but the range is -pi over 2 all the way up to pi over 2. And so we're not dealing with 7 pi over 4 right here. We are dealing with -pi over 4. Okay? And that is basically our answer. Now, when we're dealing with arc sine of root 3 over 2. Now remember, root 3 over 2 is approximately, if you're curious, root 3 is 1.732 to 3 decimal places. Root 3 over 2 is 0.866. Okay. So if we're looking for that, remember that, if you can see it closely, this is 1/2 and this is 1. This is 0.9, so it's just before 0.9, right about here. And basically what we're doing is we're asking what the output is when the input is just a little bit less than 0.9. And it's that point right there. Okay. Now, we kind of go over here, and it's going to be a little bit more than 1. Well, we know that that's basically, it's pi over 3, okay? And when we're dealing with it in terms of the unit circle, again, like tangent, it's -pi over 2 to pi over 2. Now, unlike tangent, it actually includes those points, right? On arctan, you have asymptotes at those points. But you're asking yourself, where is sine root 3 over 2? And, it's way up here, and it's this point right here. And that, if you remember correctly from constructing the unit circle, was pi over 3. Okay, so that is our one single answer for arc sine root 3 over 2. Now, as we'll see later, if you were given something like If you were given something like sine of x is equal to root 3 over 2, and you were then asked to use inverse trig in order to solve for the variable, you would get more than one answer. But as this is defined according to arc sine as a function, you get one and only one output, and according to the way that the domain and the range have been specified, that answer is pi over 3. Now, of course, your buttons in your calculator are programmed according to the function. So if you were to actually put either of those answers into your calculator, and if you were looking for the answer to them, your calculator would give you the function output, because your calculator is not going to give you an infinite number of solutions. It's going to give you that one solution. Now, of course, we'll talk about it a little bit later, but if you're looking for those infinite number of solutions, you're going to have to figure out another way to do it. All right, let's go ahead and look at this one. Inverse cosine of 1/2. Okay, we're looking that right there. Okay, and we're looking for what is the output. The output is a little more than 1. Well, that kind of makes sense, because where cosine is 1/2, sine is root 3 over 2. It's probably going to be pi over 3. So let's go ahead and look at it in terms of our unit circle orientation. Now remember that when you're dealing with a unit circle, cosine exists only in the first and second quadrant. And if you're looking for cosine, remember that you're basically looking at horizontal displacement. And so, we basically, where x is equal to 1/2, we draw a line up, and the angle measurement that corresponds with that is that very familiar pi over 3. Okay. Now, let's go ahead, excuse me, let's go ahead and look at some of these without all the doodads and the pictures. We may have to supply our own, or we may be able to figure it out all by our lonesome. Now, looking at arctan of root 3 over 3. Now, that, when we get to tangent ratios, they're not quite as familiar to us as sine and cosine ratios, but you need to remember that because tangent is sine over cosine, then basically you're looking for a tangent ratio of negative root 3 over 3, which, by the way, came from negative 1 over root 3 before it was rationalized, which can be sort of unreduced to either negative 1/2 over root 3 over 2, or positive 1/2 over negative root 3 over 2. And of course the top one being our sine ratio. So basically, if you're looking for this, you're basically asking yourself either where is the sine ratio negative 1/2 and the cosine ratio root 3 over 2, or where is the sine ratio 1/2 and the cosine ratio root 3 over 2. Now, that only happens once within the range for arctan. So, okay, well, let's go ahead and figure out. Now, remember that we've just done some problems where we're looking for arc sine of root 3 over 2 and arc cosine of 1/2, and those were at pi over 3. So this is the other side of that quadrant where the order pairs are reversed. Okay. Now sine is 1/2. Sine is negative 1/2. Basically, tangent. Well, it's going to be down in the fourth quadrant, because in the first quadrant tangent's positive, and in the fourth quadrant, negatively, of course, it's negative. So we're looking to where sine is negative and cosine is positive. So it's that one right there. Okay, well, we know that the reference angle is pi over 6. We know it's in the fourth quadrant. That simply means that it's negative pi over 6. I don't mind if you use your calculator to check your answer. I don't know to what extent I'll allow it on tests and stuff like that, but for right now, we're just getting used to these concepts. So if you do, negative root 3 over 3, boom. Okay, now that may not mean anything to you, but if you go ahead and do the negative pi over 6 as well and recognize the fact that they are both the same, then you've kind of confirmed for yourself that you've gotten the right answer. Now, let's look at arcsine of -1. Where is the sine ratio -1? Well, on the unit circle, all right, sine is -1 down here. Okay, but remember that all of this is bye-bye, and this is negative pi over 2 and not 3 pi over 2, because it goes from negative pi over 2 to positive pi over 2. So in that instance, that one actually winds up being relatively easy. Okay, well, where is arc cosine 0? Okay, well, again, let's go ahead and look at the unit circle. Where's the cosine ratio 0? Where's the back and forth 0? Well, here and here. But for our cosine function, that sort of doesn't exist, okay? And so really it's pi over 2. Okay, let's go ahead and let's move on and let's entertain some questions of this variety. Now remember that trigonometric functions exist in order to translate the sort of around and out measurements into up and forth, up and down and back and forth, right? And so, you know, sine of theta, if we have something like sine of theta or cosine of theta, basically a trigonometric expression, right? Trig expression, what does it express, right? Trig expression is like, you know, sine theta, cosine theta, you know, etc. These are ratios, right? So when you just have them sitting around as these expressions, they stand in for ratios, okay? Your inverse trig expressions, they are like, you know, arcsine of x, or, you know, arc tangent of x, you know, etc. They are angle measurements. Okay, so basically when you look at a problem like this, this right here is an angle measurement. But here's the thing, you don't actually have to find this angle measurement in order to use the angle measurement. And here's what I mean by that. Here, let me zoom in just a smidge. You are worried about finding the ratio of sides. And in this case, since you're dealing with arctan and it's positive, you're up here in the first quadrant. And I'm not going to do this necessarily to scale. I just want to basically put a triangle here in the first quadrant. And we'll call this angle measurement theta. Okay, if I were to actually go to my calculator and look at the arctan of 0.5, I could actually get an answer. Okay, now that's in radians. And then if I wanted to, I could, you know, do the secant, so 1 over cosine of that answer, and I could get the secant. Okay, 1.118. But I know that ultimately what I'm looking for is not the angle measurement, but the secant of the angle measurement. And if this is 1 and this is 2, right, opposite over adjacent, then this is going to be root 5. And my secant is going to be my hypotenuse over my adjacent. And let's just see whether that gives us the same thing. We have root 5 over 2. Boom, there you go. Okay, the only thing that you need to be very, very careful about is putting it in the correct quadrant so that you get the correct sign, SIGN, the correct positiveness or negativeness for your answer, okay? Alrighty, let's go ahead and let's look at this one right here. Now, arcsine it's a positive ratio again, so we're up here in the first quadrant. Yay, first quadrant. If it were negative, of course, we would be, somewhere else. Okay, so let's go ahead and draw ourselves. And remember that this right here is an angle measurement. That is representing this theta right here. And if the opposite is root 2 and the hypotenuse is 3, then this right here squared is 9. This right here squared is 2. 9 minus 2 is 7. So this winds up being root 7. And if you can't do that in your head, just remember that it's, we'll call this A for adjacent, or just, A, B, and C, or whatever. If you have A squared plus root 2 squared is equal to 3 squared, then you have A squared is equal to 9 minus 2, or 7, and therefore A is equal to root 7. And since it's in the first quadrant, it's, positive. And then all I need to do is adjacent over hypotenuse, and I have root 7 over 3, done and done. Okay. Now, we can basically fold in a little bit of a wrinkle when we replace just numerals with variables. But, variables are numbers, so they should behave the same way. Now, because you don't really have you don't have the ability to discern whether x is positive or negative. You can't really anchor it in a particular quadrant, so you just draw a triangle, quadrant free, just for a visual. Okay, but this is still standing in for a theta measurement for a particular triangle. Okay. So you have opposite over adjacent, x squared plus 1 squared. You take the square root of that, and you get the hypotenuse. And basically, if you want the sine of that angle, then it's just 1 over the square root of x squared plus 1. And you read it right off the triangle as if it were numbers, okay? Because they are. They're just unknown to us at present. Now, here we have arc sine of that ratio. And basically the only stumbling block in that is just recognizing the fact that 1 minus x is a ratio by plopping it over 1, which, once you've seen that once or twice, shouldn't really be all that difficult. Again, this right in here is representing an angle measurement. If I have 1 minus x over here, and I have 1 over here, now you may need to actually do a little bit of work down here in order to do this. This one's a little bit more difficult than 3 and root 2. So I have 1 minus x squared plus a squared is equal to 1 squared. Well, the great thing about squaring a binomial is that 1 minus x quantity squared is the same thing as x minus 1 quantity squared, and it's x squared minus 2x plus 1 is equal to, or plus a squared is equal to 1. Okay, well, those are, you subtract 1 from both sides, you're going to get that. And so you get a squared is equal to 2x minus x squared when you subtract both of those terms to the, from both sides. And you get a is equal to the square root of 2x minus x squared. Now, if a is equal to that, and the secant is hypotenuse over that, then we just have 1 over the square root of 2x minus x squared. Okay. Now, since we have learned the trigonometric, the inverse trigonometric graphs, for, the graphs for the inverse trigonometric functions, is probably a better way to put it, we can actually, if we are asked, put transformations on them. That's not that big of a deal. Now remember that, of course, we would have to do the parent here real quick. Now remember that if you're thinking about the parent, y is equal to arc sine of x, our domain, okay, our domain is what values can be plugged in, right? Well, that basically means that it's now -1 to 1. My range is what angle measurement values am I going to potentially get out. And remember, that was limited to negative pi over 2, because we had to basically artificially limit the domain of the sine function in order to take the inverse. And this was the artificially limited domain of sine, so it becomes the range of arcsine. Now, let's go ahead and we can and let's do this as negative pi, this as pi, and of course we'll do, we have to scale the x, the inputs, according to integer values. And so our arcsine should look something like this. Okay. And of course you could plot those a little bit more accurately, but I'm not interested right now in it being super accurate. I just want to show that this can happen, right? And so basically you're going to get a horizontal stretch of 2 and a vertical stretch of 3, which basically means that, you know, these points are going to stretch out and then they're going to triple. So what we have here is something that looks kind of like that. And sorry, it goes right over the original, okay? But it's a graph, right? It's a function. It's a function that has been defined. We can identify it as a parent, and then anything that is done to that function can be recognized as a legitimate transformation of that graph. I know that's not really, you know, that's kind of underwhelming, and I appreciate that, but I'm just trying to sort of emphasize the graphical aspect because, I don't know, I just find it to be important. All right. Now, related, of course, to transformations is what are known as combination functions. So if I have, let's go ahead and do g of x is my pink one right here. Okay, if this is 2 arctan x, which is basically a vertical stretch of 2 on the original arctangent function, and we have this right here as negative x, y is equal to negative x, what would happen if I were to take those two functions and add them together? And the reason why I'm interested in doing this, it's not academic. It basically has to do with the fact that a lot of the functions that we're going to encounter next year are going to be these styles of combination functions. And the more we are used to recognizing what these combination functions mean and how exactly they would impact the graph, the better we are at being able to reckon with these mathematical phenomena and sort of understand them a little bit better. Now remember that when I'm doing a sum function, when I'm doing any combination function, what am I combining? Well, I'm combining the outputs, okay? So at any particular value, I'm adding the outputs together. So if I go over here to 1, I'm taking this output and adding them together. Now, I went ahead and redid it down here with h of x, and h of x is actually shown right here. And because of the way that arctan is sort of more aggressive right here as it goes through and then flattens out, you get values for arctan, at least between here and here, that are more positive than these values are negative, and that's why you have this positive output right here, okay? And so basically what happens is at any particular point, like at 1, you have this value right here, and you have this negative value on f of x. Okay, well, notice that this and this, basically the point on the pink graph is farther away. How much farther away? Oh, about that much farther away. okay? And so you get something that looks like this, because at every single point, as this graph sort of flattens out and stops increasing so aggressively, this continues to decrease at exactly the same rate, which is why this slope will continue to basically get steeper and steeper and steeper and mirror this one closer and closer and closer the farther you go in terms of positive x. And of course, something analogous happens in the negative direction. I don't want to basically harp on this for too long, but I every once in a while I will make recourse to stuff like this because I do want to be able to say something like, okay, we all know what this graph looks like, right? And have all of you kind of nod, okay? And that's pretty important to be able to approach these mathematical phenomena from as many perspectives as possible, and this graphical just being one of them. Okay, that is the supplementary video for day 1 on inverse trig, dealing with inverse trig as a function. In the following videos, we're going to be dealing with inverse trig day 2 stuff, which is dealing with inverse trig as an operation. And that is going to have a little bit more payoff for us, and that's why there's going to be more than one video on that. And I'm also going to go over a lot of the style of questions that are going to be that you're going to be responsible for on future assessments. So, as always, if you have any questions, guys, please do shoot me a message or an email, and I will do my best to answer it promptly. Bye, guys.